to another round of online Newton 1665 seminars. And our first speaker today is Mikhail Shaposhnikov. So please, floor is yours.
Okay, thank you very much. Well, this is the first time I given this type of seminar. It's thank you very much for invitation. What's the topic of my talk today is standard model meets gravity, electroweak symmetry breaking, and inflation. And yeah, this work is based on 4 papers. So 2 of them are written together with Andrei Shkerin, and these are the reference. They're 2 years old. And it's also based on 2 other works, which are pretty much recent, and they are written this year, together also with Andrei Shkerin and Sebastian Zell. So what I'm gonna do, I'm going to start from introduction and motivation, and I will share with you my view on naturalness. Then I will talk about semi-classical relation between the Fermi and Planck scale. Then I very shortly discuss how the model which I will consider can be, how inflation can be embedded in this model. And finally, I come to conclusions. Okay. So introduction and motivation, naturalness. So everybody knows that the standard model is now complete. The very last particle, the Higgs boson predicted by the standard model, has been found. No significant deviations from the standard model have been observed. And with experimental values of masses of top quark and of the Higgs boson, the standard model is a self-consistent effective field theory, which may be valid all the way up to the quantum gravity scale M Planck. Okay, at the same time, the standard model was said to be unnatural. And so for me, naturalness is a rather technical criterion, which can be formulated in the following way: that the physics or at electroweak scale or right above it should be organized in such a way that quadratic divergences in the Higgs boson mass are eliminated to remove the sensitivity of the Higgs mass to physics at very high energy scale, such as grand unified scale. And if this doesn't happen, then the theory is called unnatural and fine-tuned. And normally, this is expressed by showing this type of diagrams. So we take the diagrams which contribute to the Higgs mass. We consider loop corrections coming from the standard model particles, in particular top quark, and then some new physics is added right above electroweak energy scale in such a way that the sum of the first graph and the sum of the second graph are cancelled, and you will get some small correction. Okay, so let's try to remind ourselves from where this problem is coming from. Because, okay, just saying that we have something which is quadratically divergent, it doesn't make any sense, okay? Because quadratic divergences are the matter of some regularization. So there should be a more physical way to express what the hierarchy problem is. And I would say that the origin of this problem comes back to grand unification. And it first appeared back in the beginning of 70s, and this is the paper by Gildener, which started this era. Okay, so what happened in the beginning of 70s? In the beginning of 70s, grand unified theories of strong, weak, and electromagnetic interactions were created, and this was actually the first time in history of particle physics when the particles with enormous masses appeared in the theory. So in grand unified theories, these particles are lepton quarks. They appear in this theory because strong, weak, and electromagnetic interactions are unified. And this very large energy scale, 10 to the 15 GeV, it came basically from two requirements. So one requirement is the gauge coupling unification. You look at the behavior of different couplings, you find that they meet at a scale of this order of magnitude. But not only that, this very large scale appeared because of phenomenological requirement, stability of matter. Once you have grand unified theory, then the proton there is unstable. You require that the lifetime of the proton is big enough. And then this only happens if this new energy scale, mx, is very, very large. Okay, so first of all, we got this particles with very, very large energies. It was, of course, immediately realized that if you have grand unified theories, then to have two very distinct energy scales, the Wick scale and the Planck scale, is a result of fine-tuning of initial Lagrangian. But not only that, as Gildener realized in '76, if you make this fine-tuning in tree approximation and then start to compute radiative corrections to this fine-tuning, you find that you have to fine-tune not only tree diagrams, but one loop diagrams, etc., up to pretty high order of perturbation theory. Okay, so of course, everybody knows that there were many solutions proposed to the hierarchy problem, to naturalness, to absence of quadratic divergences in the Higgs mass. And these are, for instance, low energy supersymmetry, where you have compensation of bosonic loops by fermionic loops, or you may have composite Higgs boson, where you have new strong interactions with the confinement scale of the order of Electroweak scale, or large extra dimensions. That's all these approaches, they require new physics right above the Fermi scale, which was expected to show up at the LHC, but it didn't. Okay, so it seems to me that it's time to change the paradigm. And how I think the things. So the source of a hierarchy problem, the original source of hierarchy problem, was where heavy particles with substantial coupling to the Higgs boson. Okay. Now, if there are no these particles whatsoever, we don't have large perturbative contributions to the Higgs mass diagram. And so these contributions are absent altogether. And perhaps this is the criterion which solves the hierarchy problem. So the solution is as simple as no heavy particles at all from the Wick scale to the Planck scale, okay? No perturbative contribution. There could be other contribution, but that remains to be seen whether they are dangerous or not. Okay, so if this point of view is accepted, then all new physics, and we do know that there should be new physics, should be below the Planck scale. Okay, so the proposed change of the paradigm is the following. So first of all, no new particles from the weak scale to the very high energy scale, such as the Planck scale. And secondly, UV physics, such as gravity, should be organized in such a way that the Fermi scale is much smaller than the Planck scale. So this is certainly a logical possibility. So one possibility is kind of traditional thinking about hierarchy problem, that we organize our low energy physics in such a way that high energy physics is irrelevant for that. But another possibility is that it is the high energy physics which establishes it, which gives us the small value of the weak scale. But I should stress here that when we talk about the Planck mass is not a mass, okay? It's a strength of gravitational interaction, and m Planck is not the mass of any particles. It gives just the interaction strength of gravity, and graviton is always massless. Okay, so as I said, this point of view is challenging because we do have, we must have deviations from the standard model in neutrino physics, such as neutrino masses. The standard model cannot explain baryon asymmetry of the universe. The standard model doesn't have any dark matter, so there must be something. So according to this paradigm, this something should be below the Fermi scale. But there is an existence proof. There is a relatively simple theory, which is the standard model plus 3 right-handed neutrinos with masses below the Fermi scale, which actually addresses all the phenomenological problems of the standard model. The 3 new particles, N1, N2, and N3, right-handed neutrinos, they can simultaneously explain all neutrino experiments, neutrino masses and oscillations. They can produce baryon asymmetry of the universe. They provide dark matter candidate, and the Higgs boson of this theory can play the role of inflaton, and it can inflate the universe. And that's basically all the phenomenological problems of the standard model, which we would like to address. Okay, now we got a theoretical question. So why the weak scale is so much smaller than the Planck scale? Okay, and so the ratio between weak scale and the Planck scale is pretty small, and we can ask ourselves, are there any places in physics where very small numbers appear in a reasonable way, in a natural way? And the answer is yes. Okay, perhaps there are quite a number of examples, but the example which I'm going to talk about is quantum tunneling. Okay, so in quantum tunneling provides us with small numbers in few situations, so some of them are very well known. So the first example is the gamma theory of alpha decay, in which uranium decays into thorium and alpha particle. So naively, you would expect that the decay width of this should be of the order of binding energy of proton and neutron in Stein nuclei, several mega electron volts, but in fact, gamma is much smaller, and it's much smaller because to create alpha particle, the alpha particle should penetrate through the potential barrier, which is associated with electromagnetic interactions, and that gives us that the width is equal to the binding energy times small exponential. Another example from, so to say, molecular physics is associated with tunneling in the double well potential. So in this way, you can create the transitions between states with the frequency, which is much smaller than the typical frequency of atomic transitions, which is of the order of few electron volts. So perhaps we have something similar in the standard model, so that the mass of the Higgs is equal to Planck mass times some exponential, and here we have some action, tunneling action of the order of 72. Okay, so can we imagine the theory in which this type of hierarchy may rise and may be associated with tunneling? Okay, so what I'm going to argue that most probably this type of theory may exist, and in fact this theory is something very simple. Okay, so our goal is to see, can it be that mh over m Planck is exponential minus s, and this s is something like 36. Okay, so the natural proposal along this line would be a theory in which there is only one fundamental scale in nature, m Planck, and the Electroweak scale is generated from it in a non-perturbative way. Okay, so non-perturbative, for me it will be semi-classical, because only in this way we more or less understand how to do computations. And we can immediately formulate the requirements to the theory in this case. So first of all, if we say that there is just one scale in nature, m Planck, then we should require that in perturbative theory, if we do just perturbation theory, the Higgs mass must be equal to 0. Okay, because if it's not the case, then perturbative corrections are obviously larger than non-perturbative corrections. And if there are perturbative corrections to the Higgs mass, then the goal is not going to be achieved. And so that's a very important requirement number one. And of course, the second requirement in this theory, there should exist semi-classical configurations which are leading to non-zero value of the Higgs vacuum expectation value, and this Higgs vacuum expectation value must be much smaller than the Planck scale. Okay, so let's first discuss the first requirement, that perturbatively mass of the Higgs boson is equal to 0. Okay, is there any symmetry which get enhanced if we take the standard model and put the mass of the Higgs boson to zero? Okay, so the answer is yes. There is such a symmetry. This is a scale invariance, and if we take classical, I stress here, classical standard model, where a mass of the Higgs boson is equal to 0, then this theory, in addition to all these gauge and Lorentz symmetries, Poincare symmetries, is invariant with respect to dilatations. So what you do in dilatations, you stretch the coordinates and you multiply all the fields by number to some power which is equal to canonical dimensional of the corresponding field. So in fact, the symmetry is even wider than that. It's the theory becomes to be invariant with respect to complete conformal group. So this is an interesting symmetry. It appears when the Higgs mass is equal to 0. And of course, it's tempting to use this theory for solution of hierarchy problems. And there were many attempts starting from Christoph Pettery and Bill Bardeen in beginning of 90s. Okay. Well, besides that, the classically and quantum conformal theories, they were very interesting. They do not have explicit mass parameters. They have only dimensional-less coupling. They may have good UV behavior, etc., etc. Okay, and what is interesting for us is that if we take the theory, which is scale invariant at the classical level, then in this theory, the Higgs mass can be predicted, and to be more precise, it can be expressed through vector boson mass. And here I refer to a famous paper by Coleman and Weinberg, which exactly proposed that. And well, I guess everybody know this paper. So what this paper was about, you take the abelian Higgs model, you put mass of the Higgs boson to 0 there, and then you find out that there is a symmetry breaking in this theory due to radiative corrections, and you find out that the Higgs mass is predicted, and well, in this particular theory, it's proportional. This ratio, mass of the scalar divided by mass of the vector, is proportional to the fine structure constant. So let me go very, very quickly through this theory, and then I will come to my main point. Okay, so what Coleman and Weinberg done, they took a abelian Higgs model with the scale of self-coupling lambda of the order of g to the 4th power, and the Higgs mass equal to 0. The scale invariance in this theory is anomalous due to, if you want, dimensional transmutation, or due to conformal anomaly, scale anomaly, whatever name you prefer. So the breaking of, so this dimensional transmutation or breaking of scalar symmetry occurs logarithmically. To make the argument very simple, take dimensional regularization. In dimensional regularization, all counter terms are proportional to the coupling constants of the theory. The mass is also a coupling constant of the theory. And if you take mass of the Higgs boson equal to 0, then the renormalization group equation for the Higgs mass is proportional to the Higgs mass itself. If you put Higgs mass equal to 0, then the Higgs mass doesn't run. It's equal to 0. Well, not the Higgs mass, but the parameter corresponding to the Higgs mass doesn't run. It doesn't require any renormalization. All counter terms associated with this divergence are put equal to 0. Put equal to 0. And therefore, this parameter can be predicted, to be more precise, expressed through other parameters of the theory. Okay, and that's exactly what happens here. You compute Coleman Weinberg effective potential. You find that the theory is in the Higgs phase. You find out the WEF of the Higgs field there, and then you find out the ratio between the mass of the Higgs and mass of the vector particle. Okay, so everything is predicted. So this was, and this is a very interesting idea. And of course, many people tried to apply this idea to the standard model. Okay. Here is the list of people who contributed. That started from papers by Linde, Weinberg, and then many other works in this direction. And it was realized during the time when top quark was found and other particles in the standard model were found, that this idea doesn't work in the minimal standard model. Okay, it doesn't work in the standard model because what happens is that if the top mass is smaller than some critical value, then the minimum of the effective potential is generated at very small values of the Higgs wave, about 100 MeV, due to chiral symmetry breaking in QCD. And this means that this is too far from being right. Now, if the mass of the top quark is larger than some critical number, then the new minimum of the effective potential appears. It generated at the Higgs wave greater than the mass, than the Planck mass due to quark loops. And again, this is too far from being correct, okay? If the mass of the top is sufficiently small, you can still have electroweak symmetry breaking a la Coleman and Weinberg, but then in this case, the mass of the Higgs boson should be too small. It should be smaller than 10 GeV, and again, this doesn't work. Okay, so the conclusion is that the idea, this type of idea, you start from classical theory, conformal invariant, then you break conformal invariance by radiative correction. It fails, and it looks like for it to work, you need the extension of the standard model. You can introduce extra gauge bosons, extra fermions, extra scalars, etc., etc. But this whole activity kind of misses the following fact, that the standard model is not allowing theory. We also have gravity. And in gravity, we have a huge dimensional full parameter, M Planck, which is much, much larger than the Higgs mass. This very large parameter does break scale invariance, it does break conformal invariance, and therefore it must be taken into account, okay?
Excuse me, just to remind you that you have 15 minutes left.
Yes, that's fine. So this must be taken into account, and it was not taken into account, okay? And the rationale why the Planck scale was not taken into account can be traced in the following way. So suppose that you use mass-independent regularization, renormalization, such as dimensional regularization. And then you compute the corrections to the Higgs mass coming from gravity. And then again, in this particular regularization, all corrections coming from gravity will be suppressed by the Planck scale. And the RG equation, which I written before, that the scale derivative of MH is proportional to MH, remains in force. So if you put mass of the Higgs boson to 0, then it will stay 0 if we only consider perturbative correction. So it looks like that the gravity plus conformally invariant standard model is an ideal playground for looking at non-perturbative generation of the weak scale, because in this theory, if we put Higgs mass to 0, it's not going to be generated by perturbative radiative corrections. Okay, so now let's consider what gravity will give us. So the theory I consider is the standard model plus gravity in Palatini formulation. So Palatini formulation will happen to be quite important in what follows. So just a few words about that. So in this section here, which I introduced, I neglect completely fermions, gauge bosons, etc., because they will not be essential for the argument. So what Palatini formulation of gravity is? In Palatini formulation, the metric and the connection are considered as independent variables. If you take a non-minimal coupling to of the scalar field, the Higgs field, to gravity equal to 0, then Palatini gravity is exactly equivalent to the standard metric Einstein gravity, but this is not the case in if non-minimal coupling is present. But non-minimal coupling should be present in any event because it's generated by radiative corrections. Okay, so what our goal is, we want to compute and estimate the vacuum expectation value of the Higgs field, considering including gravitational degrees of freedom, and then this can be written as this path integral where we integrate over all field. Okay. So what I'm going to do here, I'm going to use Euclidean formulation of gravity, though this is a tricky point because Euclidean formulation of gravity functional integral is not very well defined because the action is not bounded from below, etc., etc. There are all these known problems. I don't have any good argument why Euclidean gravity may work here. Maybe it can be derived through some kind of analytic continuation, but I will just join the crowd who consider it the Euclidean path integral in this theory. Okay, so what we are interested in contribution of large values of scalar field phi to this path integral, because for phi much less than the Planck scale, gravity is irrelevant. Perturbation theory works well, and we know that Coleman Weinberg mechanism doesn't work. Okay. So we want to consider very large phi, much greater than Planck scale, and let's see what kind of theory we have in this case. Okay, so if we look at our initial Lagrangian, when phi is very large, M Planck can be neglected, and then the theory which we get is actually scale invariant, and it's written here. So that's an interesting theory where the Planck's mass is dynamical and proportional to psi phi square. How to make a computation in this limit? So we conjecture that when phi field is very, very large, then it's better to change the variables in such a way that instead of this action, which is written in so-called Jordan frame, we write this action in the Einstein frame, in which the Planck scale is not dynamical anymore. Okay, so it's trivial to go from one scale, from one frame to another. You can make the change of the metric with this type of conformal factor. You can redefine the scalar field in such a way that you will get a canonical mass term, and as a result, you get this action here. But that's not the whole story, but what is very, very important here, that when you start from initial path integral, when you make this change of variables, you modify the scalar field. And instead of just phi x, you will get here this type of exponential. From where this exponential is coming from, it's just the inversion of this formula. So phi is equal to hyperbolic sinh, and then high will be, so at large values of high, phi is an exponential function of our new field. And what does it mean? That means that the part of the stuff which was not in the exponential, this phi x, it was just averaged. In new variables, we will get this exponential factor. And what does it mean? That means that the action is modified by the source term, and so equations of motion are modified. And therefore, the saddle point problem is changed. Instead of minimizing the original action with respect to field phi, we'll have to minimize the action plus the source term. Okay, so this is not a new phenomenon. Okay, so there are many places where this happens. So for instance, if you want to make a computation of integral x to power n e minus x squared for large n, you better include logarithm of x into the power here. The same problem occurs in multi-particle production. The same problem occurs in the proof of confinement of three-dimensional Georgi-Glashiev model when the source term is introduced. Okay, and so what we are going to do, we are going to find out the minimum of our action in the presence of this new thing. And now you see that the action start to depend on this parameter xi. The larger xi is, the larger is this source term. So technically, as kind of straightforward, you find out the equations of motion, and these equations of motion contain this source term. Then you find the solution, and if this classical solution has sufficiently large action, W here, then you find that the Higgs wave is equal to the M Planck. M Planck is introduced here by dimensional reasons times some number, which can be large or small, depending on the classical solution which you find. Okay, so if you find that this number is large, then you achieve the goal. Then you found that the Higgs wave is small. If you found that the action is of the order of 1, then you see that the Higgs wave which is generated is of the order of Planck scale. And so in this case, your UV physics is organized in such a way that there is no light physics whatsoever. The Higgs wave is very large. Okay, and the kind of amazing thing is that if you take the Lagrangian, which I started with, Pelletini gravity plus the standard model, you write down equations of motion. There is some technical point here, which can be easily cured, which is the following. The equations of moment contains different delta functions because this source term is integrated, this source term is local, so that solution is singular when R goes to 0. And in fact, this singularity can be removed by introduction of higher dimensional operators. Okay, so there is a large class of higher dimensional operators which can be introduced here. So here is an example. You have d mu phi to the 6th power with some coefficient of the order of 1 and all other factors which are natural. And then what you find is that the correct action, which leads us to the hierarchy between the Higgs wave and the Planck scale, is achieved for sufficiently large values of non-minimal coupling xi and the amplitude of this higher dimensional operator of the order of 1. Okay, so what this plot shows the horizontal axis is logarithm of xi, vertical axis is logarithm of delta, and this line here correspond to the action which would give us the correct Higgs wave. Okay, so the conclusion from here is that the hierarchy between the Planck scale and Fermi scale is a natural phenomenon when the standard model is classically conformal and non-minimal coupling is sufficiently large. So, so here it could be 10 to the 6, 10 to the 7 Okay, so this is the theory. We can ask ourselves whether this theory is good for anything else, and it's good for inflation. And since this point has been already discussed in the literature, and it was also discussed in our paper with Andrei Shkerin and Sebastian Zell, and since I'm running out of time, I will go through this part very, very flashy, very, very quickly. So we are talking about Palatini-Higgs inflation. Palatini-Higgs inflation is actually a single field inflation on this type of potential. It leads to the following predictions. It gives the scalar index the same as in the metric Higgs inflation, 0.97, whereas the amplitude of gravitational waves is much, much smaller than that in the Higgs inflation. In this theory, reheating happens almost instantaneously and leads to Big Bang at the temperature of the order of 10 to the 13 GeV. This theory is very interesting because the theory gets strongly coupled at the scales which are smaller than inflationary scale, so that in this theory, everything can be computed reliably. And it's the large value of parameter psi, which is required for Palatini-Higgs inflation, is also required for the explanation why the weak scale is so much smaller than the Planck scale. And so I'm coming to my conclusion is that very small MH over M Planck ratio is perhaps telling us that there are no new particles with masses between the Fermi and Planck scale, that the smallness of the Fermi scale is a semi-classical non-perturbative UV effect associated with gravity and new type of instantons. The theory based on Palatini formulation works very well. And yeah, Palatini-Higgs inflation is different from metric Higgs inflation in terms of predictions. There are open problems, of course, but we cannot make a solid prediction of the ratio MH over MP, as this depends on the details of UV theory, though we find that the crucial values which appear there, such as value of psi and the value of high dimensional operators, are quite natural. And of course, the whole discussion was semi-classical. And if there are other effects, non-perturbative, such as effects associated with black holes, for instance, we don't have a clue what their contribution is. Thank you very much for your attention.
Thank you very much for the talk. So are there any questions?
It's Alberto Salvio. Can you hear me?
Yes.
I wanted to ask, let's say, so we have some solution with gravity and the Higgs, as far as I understand.
Yes.
To ask if this solution, the curvature of this solution, if it's large, small, or of the order of the Planck scale. What is the size of this solution, or the curvature of this solution?
Okay, they are
mu nu.
Yeah. Okay, so this solution is singular. And this means that okay, this solution still has a finite action. So there are no singularities in the action, but the, say, Riemann tensor for x going to 0 is singular. So it goes to infinity.
Okay, but let's say when you look at the part of the radial coordinate for which the action gets the most contribution, is this curvature large or
No. This thing is within the validity of approximation. So the main contribution to the action corresponding to this solution is below the corresponding cutoff scales, whatever.
Okay, thank you.
You're welcome.
Any more questions? If not, then thank you again, and let's move on to our next